Hello, welcome to AQA A-Level Computer Science Unit 2 with me, Steve. Let's head inside and overview the video. We should be covering computational thinking, structured programming, writing and interpreting algorithms, testing, abstraction, and finite state machines. So, what is computational thinking? Let's ask my friend in the suit. Computational thinking involves solving problems, designing systems, and understanding human behavior by drawing on the concepts fundamental to computer science. Thank you, man in suit. Now you're boring, so goodbye. Wait, what? For the purposes of this video, let's say that I wanted to kill every mob in the Nether. And now, there are multiple ways you could do this, but you'd want to do it by the most efficient way. And the way we solve this is through simulation. We could create a computer simulation of the different ways we could do this, and evaluate which one is the fastest before we actually do it in real life. This is called a simulation problem. Next we have queuing problems. Now for a queue to be effective, the arrival rate must be less than the service rate for a stable system. And a queuing system is described by the arrival rate, the time between arrivals, the number of servers, and the service time. In this queue, Suit Man should be served first, then Minion Man, then Creeper Man. As a computer science student, you should also be aware of creative solutions, alternative approaches, and enumeration solutions. Iteration means repetition. Most high-level languages have 3 iterative structures, the first being a while loop. It checks the conditions at the start before entering the loop. The second is a for loop. This is usually written in for x equals n to m. It performs the loop a specified number of times. The third is a repeat until loop. Although this does not exist in Python, the condition is tested at the end of the loop. It is usually written as a repeat, then whatever you want it to repeat, and then underneath that until, and then the condition that it needs to meet to end the loop. Selection involves if statements. If the condition is true, then it will do the statements below the condition. If that condition is not true, then it will do the statements under the else. This leaves us with sequences, and sequences are essentially steps. It does one task after the other. This is a hierarchy chart. In computer science, we use these to help organize our programming. In this, the entire program would be invading the Nether, and now we can split this down into entering the portal, ending the mobs, and enjoying the peace. Now ending mobs can be subdivided into finding the mobs, equipping the weapon, killing the mobs, and collecting the drops. An equipping weapon can be subdivided again into crafting the weapon and enchanting the weapon. So the actual procedure of going through this: entering the portal, finding the mobs, crafting the weapons, enchanting the weapon, killing the mobs, collecting the drops, then enjoying the peace. There are many benefits to structured programming. Large programs are broken down into subtasks that are easier to program and manage. Each module can be individually tested. They can be reused. Frequently, modules can be saved in a library and used by other programmers. Several programmers can simultaneously work on different modules, shortening development time. It's easy to find errors in small self-contained modules. Another benefit of structured programming is that programs are easier to maintain. A well-organized modular program is easy to follow. It's easy to find out which module needs to be changed. Self-contained modules mean that the change should not affect the rest of the program, and new features can be added by adding new modules. A good algorithm has clear and precisely stated steps that produce the correct output for any set of valid inputs. They should always allow for invalid inputs and must always terminate at some point. They should execute efficiently in as few steps as possible and should be designed in such a way that other people will be able to understand it and modify it if necessary. There are some tools available to help with designing algorithms, such as hierarchy charts, flowcharts, and pseudocode. Now let's look at sorting algorithms. Sorting is a very common data operation process. There are many different sorting algorithms, from very simple ones to more complex ones. Let's start off with the insertion sort. The insertion sort is an efficient algorithm for sorting a small number of elements. It works in the same way you might sort a deck of cards. Suppose we have 6 numbers to sort. You go through and insert each number in the right place and then pick up the next one. The next is a bubble sort, which is quite frankly terrible a lot of the time, apart from if it's only a small number of items that need to be sorted. To sort a data using bubble sort, it requires n-1 passes through the array, with each item being compared with the adjacent item and swapped if necessary. Another way of sorting data is using a merge sort. A merge sort splits data, splits it again until it is in singular data items, and then compares it to the one next to it, and it merges it all back together in order. This is usually one of the fastest methods. There are 3 main types of testing: normal, boundary, and erroneous. You could look at this in the same way you look at villager trading. Now, a normal test would be giving the amount that the villager wants and then receiving the item back, causing a successful test. A boundary would be giving exactly, or on the border of whatever it wants, and then seeing whether the result back is successful or unsuccessful. And an erroneous test would be, say, giving the villager data that it didn't want. So if it demanded 3 emeralds, you'd give it a diamond sword and see what would happen then. Or even murdering the villager and then murdering the rest of its. What is abstraction? Abstraction is an important tool in problem solving. An aspect of this is information hiding. It's very useful in all kinds of simulation problems in which the real world is modelled. All the details that do not contribute to the essential characteristics are omitted. The London Underground map is a good example of information hiding. Another type of abstraction is problem abstraction. This involves removing details until the problem reduces to one which has already been solved. The actual term automation in this context refers to building models of real-world objects or phenomena in order to solve a particular problem. Computer scientists have to decide what details are relevant to the problem and discard anything else. Abstraction is a key feature of programming languages such as Python, Java, and Visual Basic. Using abstraction, the algorithms used to solve a problem are far removed from the actual machine code instructions that have to be carried out. Decomposition. Procedural decomposition means breaking a problem into a number of small problems so that each sub-problem accomplishes an identifiable task. Procedural abstraction is used to keep the actual values used in a computation separate from the overall design. In simple terms, this involves writing procedures and passing parameters. A car dealer might use a procedure for displaying a particular model of car and pass parameters for each colour, number of doors, wheels, etc. Functional abstraction is when you call a function to calculate anything. For example, abstraction is taken one stage further. Using a function does not require you to know anything about how the computation is carried out. You simply have to know how to call the function and what parameters to pass. Data abstraction. The data or information is relevant to solving a problem may be in the form of an abstract data structure, such as an array, stack, or queue. A stack, for example, is a data structure that allows items to be added or removed from the top. It could be implemented as an array and a pointer to the top of the stack. Items do not need to be removed from the array or sorted within it. A stack, an example of one, would be a paint software, would store the most recent edits by the user so he can press undo to remove the most recent edit. A finite state machine is not a machine in the sense of some physical mechanical thing with moving parts. It is an abstract representation of how something changes from one state to another in response to a condition or event. The machine can only be in one state at a time. It can change from one state to another in response to an event or condition. This is called a transition. The FSM is defined by a list of its states and the conditions for each transition. You could think of this as being at work, home, or in bed. And now, to get from home to work, you have to take the train, and get from work to home, you have to take another train. To get from home to bed, you have to sleep, and to get from bed to home, you have to wake. Work, home, and bed are states, and wake, sleep, and take train are transitions. Applications of finite state machines include robotics, the video games industry, design of digital hardware systems, design of compilers and network protocols, definition of languages, and to decide whether a particular word is allowed in a language. An FSM which has no output is known as a finite state automation. It has a start state and a set of end or accept states. If the automaton can reach a final state, it is said to accept the input. Starting in an initial state, the automaton processes a sequence of symbols and follows it to the target state. The symbols depend on the application. They usually represent events. Thank you for watching, and good luck.